Hi, this is Aryan Chaudhary. This is my Physics Lab 2, Motion of a Falling Object. So in this experiment, I'll cover 5 main things. The introduction, the motion analysis of the falling ping pong ball, computing two models for the falling motion with and without drag force using GlowScript, comparison of the actual and predicted motion, and finally the analysis. So the objective, as mentioned before, in this experiment, I'll attempt to track the motion of a falling ping pong ball initially at rest using tracker. Then I would make two computational models for this motion, one with and without drag force using GlowScript, and I would finally compare the observed and predicted values. So the system in this case is the ping pong ball, and the surroundings is everything else that interacts with it, for example, gravity and drag force. Some of the key ideas in this experiment are as follows. Newton's second law. The rate of change of momentum is directly proportional to the net force on it. Second, the drag force, which is the resistant force. And thirdly, the gravitational force, which is its weight. So, the experiment. The procedure is as follows. A ping pong ball would be dropped from rest, and then the motion analysis of the video would be done using the software tracker. The standard diameter of a ping pong ball would be used for calibration, which is 0.02 meters. The mass of the ball would be put as 0.0027 kgs, which is also standard for all ping pong balls. The initial velocity of the ball is 0 meter per second, and only motion along the y-axis would be considered. So these were the initial conditions. This is me tracking the ball. The tracking was done manually. So for the computational model, the code. Now the code was created using GlowScript and following formulas was used. Gravitational force and drag force. Now the following are the formulas used. Here the m for the gravitational force, m is the mass of the ping pong ball. G is the gravitational constant, which is 9.8 meter per second square. And J hat is the direction vector, which is the y direction, 0, 1, 0. For the drag force, B is the proportionality constant, which we'll find out later using the observed values. V is the velocity of the ball, and J hat is again the direction. So for the computational model, the initial conditions for both the code were put as the following. The initial mass, the position, and the velocity was put as the following, and G was put as 9.8 meter per second square. The direction vector J hat was put at 0, 1, 0. Now for the computational model without the drag, here we can see the value of B is 0. This means the F net is equal to W since the drag force is 0. Now formula for the gravitational force W, as discussed before, was put in the code, and position update and velocity update formulas were used for the iterations as below. The value of the F net is the weight of the ball, which therefore it remains constant. Now for the computational model with the drag, everything else remains the same except the value of B is a non-zero value, which is 0.0095. This was found through trial and error, and everything else is the same, including the position and the velocity update formulas. In this case, the F net is W plus D, which is the drag force. The value of F net in this case will not be constant since the value of the drag force increases over time, causing the net force to decrease gradually. Now the graph of position versus time for the observed and predicted motion. This is plotted through Microsoft Excel. Here the y-axis is the position and x-axis is the time. At first we can see the data from the two models are similar to the observed motion values, but gradually over time the model without the drag deviates away from the actual values. In contrast, the other model with the drag force seems to fit with the observed values. This is because the second model considers both the weight and the drag force, which acts on the ball in real life. Since the first model has zero drag, which opposes the motion of the ball, it has a higher final velocity than in real life. So some questions, what does it mean? Now, the model without drag does not predict the terminal velocity since there is no opposing force. However, in contrast, the model with the drag, we can see over time the drag pointing up, the weight equals the weight of the ball, resulting in zero net force and hence terminal velocity, constant velocity. What if? Now, if the object was initially thrown downwards, that would mean that it had a non-zero initial velocity. When putting the initial velocity as a random value, for instance 0, minus 1.6, 0, the terminal velocity came out to be 1.67 meter per second. This was more or less the same as the terminal velocity when the initial velocity was 0. This means that the terminal velocity is independent of the initial velocity. Hence, even if the object was initially thrown downwards, the terminal velocity would be the same. The error analysis. So when dropping the ball, there may have been a slight push given to the ping pong ball which would affect the accuracy. And since the ball was tracked manually, there may have been some human error in data collection. Thank you.